Hi guys, welcome to Bytecrafters. This is the first video that's going to come, and this is from Unit 1, which is Foundations of CPU Blueprinting. Okay, let's get started. Everybody has heard the terms microprocessor and controller. These are terms that we come across very regularly in everyday life. So, we're going to go one step ahead and understand how a processor is being built, how do you design, what is an architecture, and a lot of details. This is a very beginner friendly course, so I'm not going to go into the details. We'll have it we'll have it very at least for unit 1. It'll be like everybody can understand the course. That's how it's going to go. So what is a processor and what is a controller? Remember, we had discussed, uh, we had worked on Arduino. Arduino is a microcontroller. We'll be seeing that further also. But what does a controller do? All that a controller does is manage I/O. So be it actuating a, a solenoid switch or blinking an LED, it's handling the input and output devices that is connected to it. Okay, there is no reading of instructions or storing of memory or reading from that memory. There's nothing of that. It's just doing some IO operations. Okay, but what a processor is doing, what a processor does is different. It's reading data, it's storing data, and it is also performing the IO operations. So what you can say is a controller plus a memory management unit, a controller and an MMU is going to give you a processor. Okay, the very basic definition of a microprocessor can be a chip implementation of a CPU. But not all microprocessors are CPUs. There are GPUs. For example, the NVIDIA GeForce GTX and RTX 30. These are GPUs. And what do these GPUs do? These GPUs do image processing. So it could be like drawing boxes around circular objects in an image. So if a man were to do that, then he would take 10 minutes, but a computer can do it in a jiffy, like that. So that's how useful this is what I'm trying to say. So GPU for image processing. TPU is also very similar to GPU, just that it can handle more complex instructions. So it has more bandwidth, memory bandwidth. We'll be seeing all of that in the later slides. And NPU, the best way of understanding NPU and natural language programming is ChatGPT. Just imagine ChatGPT is reading so many requests. There are so many people asking it so many things, but how is it able to process all of it, right? So there comes another higher uh, level of processing that comes under NPU. And what follows next is, uh, yeah, every processor has a core processing unit, registers, cache, where it receives instruction from a single computing task. Okay. Okay, now we move on to see the types of microprocessors. Here we have three types. One is CISC, one is RISC, and the other special purpose. CISC standing for complex instruction set computer, and RISC standing for reduced instruction set computer. The reason for why CISC and RISC came about is because in the early 1970s, memory was very expensive. Computer memory was very expensive, so you had to include a lot of instructions within a very compact. You have to make coding really compact because you can't afford to write lines of code for you to execute something. So here you can see actually this example. Now what this is doing, we'll go through the entire example. This is loading. Move is nothing but loading. It's loading the value 10 onto AX. That is what this is doing. AX is the register. This 10 could be the value, or it could be the address uh, it could be a memory address from where this value has to be fetched. Okay, so let me come again. 10 here in this case is the value. The value 10 is being stored inside AX. Okay, similarly the value 5 is being stored inside BX. Okay, now what this has to do, this multiplication has to do, is it has to multiply 5 and 10. Okay, so again here the value AX, value inside of AX, which is 10, is being multiplied with value inside of BX, which is 5. That gives a value of 50, and this 50 is stored inside BX. AX is multiplied with BX and stored inside BX. So this entire instruction is telling you so many things, right? First, you take the value from of 10 from AX, and then you take the value 5 from BX, and then you're multiplying it and you're storing the value inside BX. If this were risk, then it would have translated to something like this: load AX10, load is LW, AX10, then you store the value. Risk has a lot of load store operations, and then again you multiply AX and BX. Now again store the value, SW value, inside of BX. So it's making things more simple step by step, but you are writing more lines of code. The number of lines of code is increased. So that is the main difference between RISC architecture and CISC architecture. Here are some basic differences between RISC architecture and CISC architecture. RISC is simple instructions and CISC is complex instructions. Yes. RISC is fixed length instructions, so it's all 32-bit length. And RISC is variable length. Can you guess why it's variable length? Because if you want to include a very complex instructions, that's going to do 3-4 steps. Like for example, we saw a multiplication operation. It's going to load the value of AX, then load BX, and then multiply, then store it inside BX. Is quite complex, but the entire instruction gets conveyed in just one line, right? So sys gives you that liberty for variable instructions, whereas it's not there in RISC. Again, this is highly pipelined. There's less. This is less pipeline. We'll get into what pipelining means, how it's useful in the following classes. And here you can see RISC concentrates only on load store instructions, whereas in CISC you can do beyond that. So that is what makes CISC uh, more. Of course, RISC is more user friendly, but CISC is going to have, it's going to utilize less memory and give you the best output. So you can just read through it. Moving on to practical applications of processors. Everybody knows about Raspberry Pi and Arduino, but what processor does Raspberry Pi use? Raspberry Pi uses ARM Cortex A72 and Arduino uses M3. So these are the M3 CPU is what it uses. And to the right we have, okay, before that was ARM RISC or CISC? Correct. ARM was RISC architecture. And to the right we have uh, a list of ARM architecture versions. You can just read through that. Versions 1 and 2 were very early versions. It was used only in the computers in 1980s, which was like yeah, the the Acorn Archimedes computer and all those 80s computers. And then version 3 was the first processor that was used in the handheld devices, Apple's message pad or something like that. And versions 4, 5, 6, 7, 8, all of it are being used in laptops, smartphones and all of that. We have version 9 as well, version 9. I think that came in 2022. It comes with a lot of AI and AI processing and all of that. So it's nice to see technology growing. Okay, data sizes and instruction sets. Before we move on to discussing data sizes, we have to see definitions of what an instruction set is. So instruction set, as the name suggests, it's a set of instructions that the microprocessor is going to execute in order. That is an instruction set, to put it in very simple words. And there's another term called bandwidth. Now, what is bandwidth? It's the number of bits that is processed for every instruction. That is bandwidth. So uh, the bandwidth for the RISC architecture, which is ARM, is 32 bit, whereas for thumb it is 16 bit. So it's more in case of ARM. So just to get a feel of what bandwidth is, and then clock speed. Clock speed is the number of instructions your processor is going to execute per second. So I'll repeat all three definitions. One is instruction set. Instruction set, the set of instructions that the processor is going to execute in order. And then clock speed, the number of instructions that it's going to execute per second. Bandwidth, the number of bits processed in every instruction. And when it comes to data sizes, you have RISC is 32 bit architecture, which is 4 bytes. There's actually uh, there's actually explanation for what each of it stands. 1 byte is 8 bits, half word is 16 bits, which is 2 bytes, 2 byte boundary, and word is 32 bit, which is 4 byte boundary. And these are two famous instruction sets. One is 32-bit standard ARM instruction set. We'll see ARM instruction set in detail in the following slides. And the other one is 16-bit thumb instruction set. You can imagine 16-bit thumb instruction set as a CISC mentality. So you want to have code compact, so you want to make instructions also very small. So that is 16-bit thumb instruction set. And yeah, this is how the 4-bit boundary is for the 32-bit word. Furthermore, discussing about processor modes, we have user mode, fast interrupt request, and supervisor modes. These are the four general modes. Other than that, we have about undefined system modes. Uh, you can imagine the processor to be like a theme park. So in the user mode, you are the user who wants to try out all the fun rides and all of it. So you don't have access to controlling them, but you can enjoy sitting on all rides and have fun. So it has the lowest priority. You don't get to control any stuff. Fast interrupt request is like a VVIP entering the theme park. So when he enters, it's blocked for the general public. The rides in which he wants to enjoy, they are being stopped for general public, and only he and his family can enjoy. It's like that. And interrupt request. Sometimes interrupt request mode also comes under user itself if the user has the ability to raise the interrupt. But interrupt request is a little better than the user mode. It's not like a supervisor mode. In the supervisor mode, like you can think of supervisor mode like the manager of the theme park. You may know, where everything gets to be under his control. He decides what rights to be scheduled, rescheduled, stopped. So he has control over the entire thing. So this is processor modes in general. Other than that, you have abort mode also. These three modes, or abort and undefined modes, come only when there is some violation uh, in memory access, or it could be in anything. Abort mode comes. Abort mode, you can imagine, like if there's an emergency in the theme park, then all rides are stopped and people are asked to evacuate. Okay, so similarly, if the system enters abort mode, all the processes are stopped, and the system will shut down. It'll restart. So that is how you can imagine abort mode. Undefined mode, when the system uh, handles undefined instructions. And system mode is very similar to user mode, so it's the same. uh, it uses the same, it's more privileged than the user mode, but it's the same. Based on the processor modes that we saw, we'll see how the processor is going to handle various programs. Let's say there are three user programs as shown here. In this case, in the first case, the processor is executing program 1. This could be in any order. It could start with program 2, program 3. It could be in any order. And program 2 and program 3 are waiting. So it's like a buffer. And here again, after 1 is done, the processor starts executing program 2. There is context switching between user program 1 and user program 2. And then it starts executing program 3. Now let's say when it's executing program 3 itself, you get a normal priority program. A priority program is always a one step above a user program, and a high priority program is even one step. It's like a fast interrupt request. We saw, right? Fast interrupt request and interrupt request. So it's like that. And then a high priority program takes over the normal priority. Moving on to register organization, the register bank. So we'll see there are 37 registers in ARM, each of 32-bit length. Okay, and in this 37, 7 are special purpose and 30 are general purpose. General purpose are where you can store addresses, where you can store memory. Special purposes are 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 there for a specific reason. It could be for indicating flag. It could be for holding addresses of the next instruction. We'll see what each of these special purpose registers do. Firstly, one is for the program counter. Now, what is a program counter? Program counter is going to store the address of the next instruction that is going to be executed. You can think of program counter as the guy who's standing in the queue who is about to receive the award next. Okay, the guy who's monitoring all that. So there are a lot of people standing. There's one guy who's receiving the award. He leaves the stage, and there's a guy waiting behind him, right? So who decides this? You can think of that as program counter. Program counter is always going to have the address of the instruction that is going to follow up next. So all the processor has to see is the program counter, and once the instruction is executed, the program counter updates. Okay, and there is one dedicated CPSR register. Now CPSR register is just one register, but it is 32-bit length, right? So it has so many, each bit of CPSR gives a lot of indications. It can carry, I think the low thumb state registers of CPSR carry flag values of 0 flag, carry flag. Uh, yeah, there are so many flag values. CPSR, that the 32-bit itself, each bit represents a flag value. So CPSR is very important, and CPSR changes for every instruction as well. For the new instruction that it's going to execute, the CPSR changes and it moves on to the saved SPSR, which is the saved program status register. There are 5 SPSRs. I'll repeat again. CPSR is going to contain flag values like carry flag, 0 flag, and all of them. Once the instruction is updated, the CPSR values, there's a context switch. The CPSR values move to the SPSR. There are 5 SPSRs in ARM, and other than these 7 special purpose registers, there are 30 general purpose registers as well. So coming again, there are 7 special purpose registers, 30 general purpose registers. Out of the 7, 5 are SPSR, 1 is program counter, and 1 is CPSR. Okay. Processor mode governs which bank of several banks of registers is accessible. Okay, this is something also very important. We said 30 general purpose registers, right? Not all 30 are being used by the user. Okay, there are some priority registers inside of this 30 itself. These registers include stack pointer, link register, and there's a priority program counter, and there's a priority CPSR. Now, the reason why it's called priority is because it's not available to the user, but maybe in the supervisor mode, if the processor gets to the supervisor mode or fast interrupt request mode, then these registers can be accessible by the priority. So stack pointer, to put it in a very simple way, all these registers, stack pointer, link register, priority program counter, and priority CPSR, are things that other registers can also do. Like the other 30 general purpose registers can also do. Like for example, if you see what the stack pointer does is, it is just pointing out to the memory in that stack. Whatever memory that you are accessing, it will point to that. That is all a stack pointer does. That is something any other register can also do. And a link register is used to store the functional value. Let's say you have a function a into b return c. The return value c is stored in link register. Now the return value c can be stored in any of the general purpose registers. It's there just for priority use. And same goes with program counter and CPSR. There's no change in this. So this is the register organization summary. You can look into the image also. This gives a clear view of general purpose, fast interrupt request modes, and in case of undefined and abort modes also, which of them, low thumb state and high thumb state. This is also something that I forgot to mention. Low thumb state is the 0 to 16 bits. High thumb state is 16 to 32 bits. Okay, so yeah, you can just go through this. We just saw CPSR is just one register, 32-bit wide, and each part of that register is going to convey a lot of things. This is an explanation of CPSR. So what mode it is operating. So these are the mode bits, whether it is user mode, what mode the instruction is, whether it's fast interrupt request, supervisor, abort, undefined, or system. So that is conveyed in these first 5 bits, and each of these are flags. So there's nothing much to explain here. It's more of content that has to be remembered. So this one status register is going to tell you almost everything about that instruction that you're doing, whether even the flag bits, the status bits, whether the result of previous instruction is 0, negative, is there a carry for it, and if there is overflow, that is conveyed in the 28 to 31st bits. Each of these is a single bit. So N, Z, C, V, it's either a 0 or a 1. So if let's say Z is set to 1, the result of the previous instruction is a 0. So that is what it is. And if there's a carry, then the carry bit is set to 1. So this is more of content that has to be remembered. Nothing much to explain here. Moving on, how does the processor read your program? The processor is not going to go from instruction 1 to instruction n and start doing it. That's not how it does. Let's say this is the code that you have written. Okay, now your instruction 1 gets assigned to memory 1. Followingly, instruction 2 gets assigned to memory 2, instruction 3 gets assigned to memory 3. This is where the stack pointer is of use, because the address of this memory plus 1 is the address of this memory. So what monitors these memory addresses is the stack pointer. Okay, so this is one good application of where the stack pointer is being used. Okay, once all of these instructions get assigned to memory, okay, the first instruction to be executed goes to the PC, and from the PC it gets executed. Okay, it gets executed, CPSR values are updated, PC updates to the next instruction. Okay, let me repeat. The address of instruction 1 is pointed out to PC. Okay, from the PC, the instruction is executed. The execution outcome is reflected in CPSR. PC updates itself. This is the PC updates to the next instruction. This is the flow in which this is the ARM program structure.